All righty, so you have 2 days before, 2 weeks before midterm break, and we're right where we expect to be. We'll talk about partial fractions this week. We'll talk about improper integrals next week. If we have some extra time, we'll talk about probability, and we'll have our sort of culminating integration test next week as well. So partial fraction decomposition is extremely a very specialized technique compared to some of the others. Like integration by parts, you can at least try it whenever you have a product. Do substitution, you can at least try it whenever you have composition. I mean, might not work, but they're very general techniques. Partial fraction decomposition is used in one very specific situation when you are trying to integrate a rational function. So rational functions, just the 5-second reminder, are what you get when you divide one polynomial by another polynomial. So in general, none of the techniques that we've learned can be used to integrate these. And I mean, you say something like that, and there are always exceptions, you know. This is a rational function that you could hit with u substitution, that u would be the denominator, or if you had a 1 up there, this is a rational function and it's just the arctangent. There's no work that needs to be done. So you can never make, you know, these absolute statements. But I mean, if I just sort of create one at random, we are not going to be able to integrate this. I mean, u substitution doesn't work. Going back to a comment I made on the test, if you're approaching a fraction with u substitution, you'd let u be the denominator because you can integrate 1 over u. But that falls on its face here. We don't have anything like the du that we need. It's not anything. So partial fraction decomposition breaks into multiple cases, but the idea is always the same. And actually, the idea is based on this little marginal note that we can't integrate rational functions in general, but if a rational function is simple enough, we might be able to integrate it. You know, we can integrate this, for example. And we might be reaching the point where we just do this kind of U substitution in our head. But it's a small U substitution. This turns into 1 over U du. It's the natural log of the absolute value. So the idea is that if you have a complicated rational function, hard as it is to believe after last week, I'm going to throw some of these windows open and try to get some air moving in here. The idea is that if we have a complicated rational function, we can try to write it as the sum of simple rational functions. And the idea here is that if now we're trying to integrate this, go over to the right. If we integrate the sum, we can deal with each of those terms separately. The integral of the sum is the sum of the integral. And I say that these are simple. Hopefully they look something like this, and we can integrate each of the individual terms. So that's the basis of partial fraction decomposition. And partial fraction decomposition, as I say, it sort of multiple cases. Partial fraction decomposition relies on factoring the denominator. And that's kind of an issue in general, because you know that like if you have an arbitrary quadratic, for example, I mean, where maybe you've got decimals or fractions, you know, you're not going to be able to factor most quadratics by hand. But I mean, that by hand is important. I mean, you ask how this works, you know, a lot of it in the real world, as it were, is going to be done using computers, and computers will factor polynomials for you. I mean, computer will not care if instead of nice numbers, we have messy decimals. Computer will work up to 8 digits or 16 digits or whatever the current standard is. So this requirement that we be able to factor the denominator isn't a huge deal a lot of the time. And with that observation, let's just start with the first case, or rather, no. Let me go way back here. I don't know, maybe I shouldn't skip around like this. There's a comment I want to make. I guess it doesn't really matter which frame I make it on, that the degree of the top has to be less than the degree of the bottom for this partial fraction decomposition to work. And there are ways around this. I mean, if the degree of the top is bigger, you can do polynomial division. We might do an example of that later in the week. But for now, let's just state this as something that we need. So you know, the top is degree 2, the bottom is degree 3. That's fine. We'll start with the case where the bottom is a quadratic and the bottom factors. The quadratic part isn't so important here. And the factors do not repeat. So something like x squared plus 4x plus 4, that does factor, but it factors in a kind of special way where we have the same term appearing twice, x plus 2 squared. And when I say the factors do not repeat, I'm kicking that case out. I'm looking at cases where we have, you know, x minus 2 times x plus 3, or whatever. And that top, that p of x, I'm not explicitly putting any expectations on it, but it has to either be a constant or linear, just because the degree has to be less than the bottom. And this is what I think of as sort of the, well, this is a clean case. If we have a case like this, we can have a linear expression up here. And in the bottom, we have a factored quadratic. I mean, actually, sorry for the kind of chaos. Let me actually make this a statement about fractions. I mean, it's being used as an integration tool. That's the point of it, but it's just a general statement about rational functions. That this can be written as the sum of a number divided by the first term of the factored quadratic, thus a number divided by the second term of the factored quadratic. And then going back to calculus, if we want to integrate what's on the left, well, we can integrate what's on the right. And what's on the right is something we can deal with. Both those terms on the right can be dealt with using natural logarithms. So that's the idea, and the question then becomes, well, how do you do this if we have, again, let's just not put the integral sign for the moment. If we have 2x divided by x minus 4 times x plus 3, my claim is that I can write the fraction on the left as the sum of two simpler fractions on the right. And the question then becomes, well, how do we do it? And in the majority of, well, I shouldn't make sweeping observation comments like that. I'll say that I think most situations where you use partial fraction decompositions are nice cases. By nice, I mean don't require an immense amount of work, might need a computer to do the factoring for you. And I make that observation because textbooks maybe tend to focus on messy cases where things don't work out nicely. And that makes sense. The more complicated the case, the more time you spend on it. But it maybe gives students a kind of distorted idea of how this stuff works. The method, I mean, if you ask what we need to do here, well, we need to figure out what capital A and capital B are. The method that I'm going to present today is called the Heaviside method. And for more complicated partial fraction decompositions, it might not work. But again, I don't want to focus on the super complicated examples. I want to focus on the kind of stuff you see in applications. If Heaviside, not the household name. We've seen it before, and way back in Calculus 1 when we were looking at continuity. We looked at this simple function that goes from 0 to 1 and is discontinuous at 0. And there's no real reason you'd have committed this to memory, but that was the Heaviside function. The Heaviside in question was Oliver Heaviside, beginning of the 20th, end of the 19th century. He's sort of one of these people, I'm afraid, who's best known nowadays for being wrong about something. He was one of the few major physicists to really oppose the theory of relativity, but he did a lot of good stuff too, including this mathematical trick that bears his name. So the Heaviside method, I'm going to have to move to another frame, but we're going to clear that fraction on the left. We're going to multiply both the left and the right side of this equality by that fraction. see, it's x minus 4 times x minus 3. Or was that x plus 3? X plus 3. And let me see, the denominator was x minus 4. This simplifies significantly. You see the x keep making little typos here. That was a minus. You see the x minus 4s cancel. And then the x plus 3s cancel. And this is not yet the heavy side method. This is what you'd always do, even if the heavy side method weren't going to work and you were going to try something more complicated. But the heavy side method is based on the idea that this is an equation that should be true for every value of x. And there are two values of x specifically that we can choose that are really going to simplify this. X equals -3 and x equals +4. And the reason that's going to simplify this is that each of these is going to turn an expression into 0. If we let x be -3, what happens on the left? 2 times -3 is -6. What happens on the right? And you see that one of these terms goes away. -3 plus 3 is 0. 0 times a is 0. So now you have an expression that just has the b in it, and you can solve for the capital B. B, the negatives cancel. 6 divided by 7. We let x be 4. And again, you see that one of those expressions cancels. Well, cancels isn't quite the right word, but it goes away. 4 minus 4 is 0. 0 times b is 0. We get 8 equals 7 times a. So a is 8/7. And that's the heavy side method. And as long as the denominator factors nicely without any repeating roots, the heavy side method will work. It will work, including when we, look at cases where maybe the denominator is cubic or isn't quadratic. What we really need here is that it factors cleanly. And once we've solved for a and b, I didn't frame this as an integration problem, but once we've solved for A and B, you could integrate what we have here. The integral suddenly getting a lot of detritus. The integral of 2x divided by x minus 4 times x plus 3 is the integral of, okay, a is 8/7, so 8/7 over x minus 4. Plus the integral of b is 6/7, 6/7 over x plus 3. And of course, those fractions, aren't lovely. This is very typical of the partial fraction decomposition. But both of these we can integrate. If we're not comfortable doing this in our head, we can do this as a u substitution. You see du equals dx. We don't have to mess around like at multiplying in or dividing terms. This becomes 8/7 over u. Did not leave myself the proper amount of space there, but that's 8/7, the natural log of u. 8/7, the natural log of x minus 4. And over here, it's going to be 6/7, the natural log of x plus 3. And now that we've taken those individual integrals, we just add them together. With our constant of integration. So that's partial fraction decomposition. Again, it's well, I'd say that's part of one lecture on partial fraction decomposition, but that's the basic idea behind it. We take the rational function, we write it as the sum of simpler rational functions, we integrate the simpler rational functions. Partial fraction decomposition, as I've said, is specialized. It's for rational functions alone, but it shows up in some very significant applications, which you'll see when you take differential equations, Math 330 with me. So for example, the equation of in calculus, we talk about motion without air resistance. The equation for motion with air resistance requires partial fraction decomposition to find it. So, likewise, some very famous population models, animal population models, involve partial fraction decomposition. So ordinarily, I now look at a slightly more complicated case for, I know this has happened a few times this semester, and I apologize, but I feel kind